So drawing electrons as dots, of course, is a drastic oversimplification. We already talked and learned probably more than you wanted to know about what the electrons are doing, and they're not just little dots sitting there, right? But it makes it easier to think about. So we think about the sharing of the electrons. When something is shared, it's not always shared equally. You ever shared a bed with someone? How about that blanket, right? One person ends up with more of it, right? Well, when electrons are shared, that happens also. So electrons are not always shared equally, and that gives us polar covalent bonds, where we have an unequal sharing, and so it's not an ionic bond, but one end of the bond is a little negative and one's a little positive. So if we look at hydrogen fluoride, the fluorine atom has a larger or a more strong attraction for the electrons than the hydrogen does. And so it will pull the electron density over to itself. It will hog the electrons. And so if we look at electron density, there's more electron density around the fluorine than around the hydrogen. So this end is a little bit negative, and this end of the molecule is a little bit positive. And we can indicate that with an arrow pointing to where more of the electrons are, with a positive on this side. Or we can use a lowercase Greek delta plus and delta minus. Those represent a partial positive and a partial negative charge. So electrons remind me of little boys. I have a 10-year-old boy, and electrons are kind of like 10-year-old boys. They're a little squirrely, unpredictable, right? So I think of this as two houses. There's a hydrogen house and the fluorine house. And the two boys, one from each house, come out to play. And they're not necessarily going to equally split their time between the two houses. It kind of depends on what's going on in the house, right? So at Fluorine's house, they've got the big screen TV, they've got satellite and cable, and they've got all the latest gaming systems. They've got a trampoline and a swimming pool and a soda fountain in the kitchen, and Mom will bake you a pizza or order one, whatever you want. Fun place for little boys, right? And then over here's Hydrogen's house. They have a black and white TV with some old Thomas the Tank Engine VHS tapes. And they don't even have a water dispenser or an ice maker on the door of the fridge, so you can get just room temperature tap water and bread. They ran out of butter. It's just not so fun, right? You're laughing. That's good. Okay, so where are those little boys going to spend more time? At the Fluorine house. Why? It's more attractive, more fun, right? So does that mean that Fluorine has taken or adopted Hydrogen's child? No, but he's spending a lot of time over there, right? So there's this unequal sharing, okay? So this end is going to be a little bit negative because it's not a full -1 charge, but because the electrons are spending more time over there, it's a little bit negative. So we see here we've got hydrogen fluoride molecules between these two plates. If we put a charge on the plates, electrical charge, all of these these molecules will line up so that the negative ends are closer to the positive plate and the positive ends are closer to the negative plate. These molecules are not symmetrical, and they're not symmetrical with respect to their charge. They're called polar bonds. So that ability of an atom to attract electrons to itself in a chemical bond is called electronegativity. So how cool is fluorine? Fluorine's super cool. Fluorine has the largest electronegativity of all the atoms. Electronegativity is inversely related to atomic size, so it is also a periodic trend. Fluorine is the most electronegative. The noble gases don't really form bonds, so how can you talk about how attractive they are to electrons in a bond? So we just completely leave out the noble gases when we talk about electronegativity. So this is one way to look at electronegativity. Here we've got a chart where we're showing how electronegative something is by how tall the bar is. And so here we've got fluorine at a 4.0, and that was just sort of randomly assigned. 4 is the highest, just kind of like a grade point. Fluorine's the highest. And so the trend here is as you go across a period, as you get closer to fluorine, electronegativity usually increases. And as you go down a group, it decreases. That's inversely related to atomic size. I think the easiest way to remember this is fluorine is the ultimate electronegative element. Who's closer to fluorine? That's the more electronegative one. There are values for all of these. We're not actually going to use them very much. They might show up on a homework question, but they will not show up on exam questions. You certainly do not need to memorize them. I would like to point out that there are some elements that have the same electronegativity as other elements. Like here's nitrogen and chlorine. And so you wouldn't necessarily, just predicting from the periodic table, you wouldn't realize that nitrogen and chlorine are the same electronegativity. But for our purposes, that's not going to matter. We're going to be okay with that. So, of course, there are degrees of bond polarity. So you could have a bond that's completely non-polar, equal sharing. You can have the other extreme where the sharing is so unequal that it's actually donated the electron to the other atom. And so there's a continuum from 0, where there's no electronegativity difference, up to 3.3, which is the largest difference in electronegativity between two different elements. And so we kind of have to divide this into sections, and these are somewhat arbitrary. So we say if the difference in electronegativity is from 0 to 0.4, we're going to call that a pure covalent bond or a nonpolar covalent bond. I prefer nonpolar, so it's more descriptive. And then in the middle here, from a difference of 0.4 up to 2, we're going to say that's a polar covalent bond. It's still sharing, but it's not equal. And when the difference is greater than 2, we're going to call that an ionic bond. And say, well, essentially the electrons are being transferred. So if we go back to this table, if we were looking at a bond between carbon and nitrogen, the difference in electronegativity there between 2.5 and 3 would be 0.5, right? So that would be considered a polar bond. But if we looked at nitrogen and chlorine, where the difference is 0, that would be considered a nonpolar bond. There's one that I want you to remember. So here's hydrogen with an electronegativity of 2.1, and there's carbon, 2.5. So that electronegativity difference, 2.5 minus 2.1, 0.4. So that's right at the edge of a pure covalent nonpolar bond, right? So that's hydrogen and carbon. So I want you to remember that a carbon-hydrogen bond is nonpolar. That's important because that's a very common bond in organic chemistry. That's the one that's going to come up the most that we need to remember. So carbon-hydrogen bond is nonpolar. We can measure the degree of polarity as the dipole moment. And a dipole moment exists anytime you have a separation of positive and negative charge. The dipole moment can be defined as Q times R. R is the distance, and Q is the charge magnitude. Common unit for this is the debye. So we'd like you to have heard about a dipole moment and how it's calculated and the units. We're not actually going to do this calculation, okay? We just want you to know about it. There's aspects of chemistry and other sciences where you would get into this, but we don't really need to know this too much for general chemistry. If we look at these molecules, Here's a chlorine molecule, 2 chlorine atoms. They're the same element, their electronegativities must be the same, right? So then the difference in electronegativity is going to be 0, and the dipole moment is going to be 0, and what kind of a bond is that going to be? Nonpolar. Polar means that one end is different than the other. Nonpolar means that there's no difference. So this is a nonpolar bond. If we look at chlorine and fluorine, it's not pointing at chlorine and fluorine. There we go. And the difference is 1. Okay, so is this nonpolar or polar? Is there a difference? There's a difference. This is a polar bond. One end is more negative than the other. And if we looked at this is chlorine bonded to fluorine. And if we wanted to, we could put the lone pairs in there. But I don't feel like doing that right now. So we could predict which end is going to be more negative. It's going to be fluorine or chlorine. Who's got the coolest house? Fluorine. So chlorine is going to be a little bit negative because the electrons are very attracted to the fluorine. And the chlorine end is going to be a little positive because they're not spending as much time over there. The other notation points to the more electronegative element and puts a plus over here. I think of that as mom's coming home or somebody's coming to the house and wants to know where the kids are, and dad's out mowing the lawn. And they say, where are the kids? You point, they're over there. They're Florine's house. So the arrow is pointing, that's where the kids probably are because they're going to spend more time over there. And then we've got this little plus thing on the other end, and that tells us this is the plus end. If we look at lithium fluoride, without knowing anything about the electronegativity difference, what kind of elements are those? Metal and nonmetal. And what have we learned about that sort of a compound? It's ionic, right? We learned that there was a transfer of electrons. So just based on element type, I would expect you to identify this as an ionic compound. So yes, we can do it based on difference in electronegativity. That's the ultimate basis for this. But we can also just use things that we already know. Metal, nonmetal, ionic compound. 2 nonmetals, molecular or covalent compound. So now the distinction is it going to be polar covalent or nonpolar covalent? Well, if the 2 elements are the same, it has to be nonpolar, right? Because if you've got 2 identical houses, nothing is different about them. Why would the boys go to one or the other? They're going to spend equal time, right? If there's no difference. So if you have 2 of the same element, it's a nonpolar bond. And the one I want you to remember is carbon and hydrogen. Carbon-hydrogen is also nonpolar. If you have any 2 nonmetals that are different from each other, like chlorine and fluorine, carbon and nitrogen, any other nonmetals besides carbon and hydrogen, I expect you to tell me that it's a polar bond. That's not always true, but it's good enough, and it's good enough, and that's good enough, right? We can also quantify this as percent ionic character, which just takes the ratio of the bond's actual dipole moment to the dipole moment it would have if the electron was completely transferred. So here's where we get caught out lying to you a little bit. There are actually no 100% ionic bonds. It's a little hard to understand. But we can just go on pretending that there are. So we think of all of these ionic compounds as there being a complete transfer of an electron from the metal to the nonmetal. In actuality, that's not quite the case. So if we look at percent ionic character, we would define ionic compounds as having greater than 50% ionic character. So if we look, here's a 50% line, and all of the compounds up here are metal-nonmetal combinations. We've got HF here. He's getting really close to that line, but it's under 50%. So this would be considered a covalent compound. And the rest of these are down here with less than 25% ionic character. So we can still use that metal-nonmetal ionic. Two nonmetals, covalent. Two of the same nonmetals, or carbon-hydrogen, nonpolar. Two different nonmetals, polar. So classifying as pure covalent, polar covalent, or ionic. So I have never typed this out in the slides, and so that's unfortunate. So I'll write it out here. So it's ionic if you've got metal, nonmetal. Yeah, learn how to spell. Covalent is when you have nonmetals. If it's nonpolar, good grief. Nonpolar. Same elements, same element, or carbon hydrogen. Polar, two different nonmetals. I think that's fairly easy to remember, and it works enough of the time that we don't have to worry about the little details. So this is what we're going to use to predict what kinds of compounds these are. So if we've got a bond between iodine and iodine, is that going to be non-polar, covalent, polar covalent, or ionic? Non-polar covalent. Because that's two nonmetals, and they are the same. So one is not going to take the electrons more than the other. They're going to share equally because they're the same thing. How about cesium and bromine? Ionic. Cesium is a metal, bromine's a nonmetal. This is an ionic compound. Ionic bond. How about phosphorus and oxygen? Both. You had to pick one. Polar. This is going to be polar covalent. Okay? Because we have two nonmetals, and still a covalent compound. But they're different from each other, and so one of them is going to hog the electrons. And if we look at their positions on the periodic table, who's going to hog the electrons more? Who's going to take the electrons? Oxygen. So if we drew a piece of the periodic table, there's oxygen, there's fluorine, and here's phosphorus. Who's closer to fluorine? Oxygen is. Oxygen is more electronegative. Any questions? Being able to predict whether something's polar or nonpolar is important for a lot of things to come.